Sarah. Good morning, everyone. Thank you for being here. As Jim mentioned, I'm going to talk about token binding here, which is an emerging new set of specifications that I think has a lot of promise, and go in a little bit to the details of how it works and hopefully some of the value that I think it maybe provides over time. I do want to first say thank you to Troy for starting things off yesterday with the keynote by wearing shorts and thongs and also dropping some profanity early on. It really helped me sort of feel comfortable coming up to the stage today because that's really kind of my sweet spot. So, a little photo actually from the pool the other night. Try to make it relevant for everyone here. So anyway, with that, let's get started talking about token binding. Some formalities and introductions first. First of all, as Jim said, I work for Ping Identity. I've been there basically all of my career. Ping does single sign-on, access control, MFA, things like that, which is sort of how I ended up in this space. I'm not strictly in security, but do a lot of stuff in identity, which is very much integral and related to security. So that's how I ended up in front of all of you fine people. I do product development work, and I also do standards work. So I work on new and emerging standards, and that latter piece is what gives me the opportunity to talk to people like you about new things like token binding. It's not really anything particularly special, but the opportunity to be engaged with new and emerging standards lets me learn about things that are new that haven't quite hit the market yet, and gives me something that's hopefully interesting to talk about. It also gives me the chance to wear this ridiculous shirt, which was from an Internet Engineering Task Force meeting, and they make some of the worst shirts possible. But it is Hawaiian, so I thought I'd bring it out today. I also pretend to have a different career sometimes. I enjoy photography. I shoot at events, and a lot of times when I travel for work. So it's as Cinia said about her ballroom dancing, it doesn't pay as well as development or security work, so I can't make it a real career, but I like to pretend. And so as a result of that, my presentation contains a lot of gratuitous photographs. Now there's a couple reasons for this. One is it's sort of like the old family slideshow vacation stuff where I have a captive audience here, and I can force you to look at my work, which is very gratifying for me. And the other thing is I once saw someone from a big company talk about how, gave their legal stuff and about how they were, avoiding copyright infringement and everything on their work. And at the time, I'd been stealing content from other people and putting on presentations and realized, it's not such a good idea. So by using my own content and pictures, I avoid any potential copyright infringement stuff. Now, I'm not saying that other people here this week have infringed on copyrights necessarily, but I'm just saying that my work doesn't because it's all my own work. And the usual sort of safe harbor here is that this presentation may contain forward-looking statements, and no investment or purchasing decisions should be made based solely on the content herein. That is, of course, unless you want to hire a photographer for an obscene amount of money, in which case you can go ahead and do that. Thank you, by the way. It's really helpful when people are actually engaged. It loosens up the mood a little bit. So with that, let's get started. A bearer token is a security token that has the property that any party in possession of that token, the bearer of it, can use the token to access the associated resource or whatever the associated value of that token or access control of that token is. And no proof other than just having that token is needed in order to wield it. This is where I used to watch movies as a kid, and they always would pay, the villains would take bearer bonds. I never understood what the hell that was until much later in my life. Bearer bonds, you just have the bond, you have the money, you have it's good. Or cash is another kind of bearer token that just having it is fully sufficient to wield it for all its value. They are what they are. Maybe here's a real-world example of the problem with bearer tokens. There's one truth and a lie here. These are two RSA speaker passes. RSA passes. One of them is real and based on my real actual job. The other one is a little bit more based on my aspirational pretend career. And if I hadn't told you about it, you can probably guess which is which. But in the absence of that knowledge, there's no way to tell which of these is legitimately I legitimately have the rights to wield or to wear. So it's just sort of a simple real-world example of bearer tokens and how they can be problematic. Bearer tokens in our own lives that we probably use every day on the web and likely use in our jobs and our development all over the place are cookies. And there's been a lot of things done to protect cookies from theft. but they remain bearer tokens. So there's the secure flag that you can set on a cookie, which prevents it from being sent over non-secure connections, so it can't be sent to an unauthenticated site or sent in the clear. There's the HTTP only flag, which is there to help prevent exfiltration via cross-site scripting attacks, exfiltrating the cookie to another site. Now, Mario yesterday was a little bit critical of this, noting that there's a lot of other attack vectors you can apply if you have full cross-site scripting available in there. And so just preventing the exfiltration of a session cookie doesn't necessarily protect everything against the other sorts of things you can do with cross-site scripting. But at the same time, HTTP only does prevent that one specific case of cross-site scripting being able to steal session tokens or session cookies and exfiltrate them to other sites. And these things are, they're somewhat effective. It's not like cookies are the end of the world. We use them every day. For the most part, things work okay and they're relatively secure, but they are inherently flawed, and if they're stolen, they can be reused. And despite some of these protections, it's been sort of an arms race going on. There are still times where cookies are stolen, either on a small or large scale. The most recent example I'm aware of, there's probably others, but there was a subdomain takeover on Uber towards the end of last year where it was researchers, but they were able to overtake a subdomain in the Uber system and harvest cookies that were site-wide and replay them. So despite the various protections around cookies, there are still ways to steal them and replay them. On top of that, a lot of people are kind of the new school world of single-page applications or SPA. That is me, it's okay. A lot of new development is taking this course, and while a lot of these applications could actually be protected with cookies, sort of, the authorization and session controls could be done with cookies. A lot of app developers are doing different things around OAuth to maintain sessions. Sometimes they need to for cross-site ability, sometimes they don't. But regardless, there's some of a trend towards holding session tokens in local storage. And that puts us right back into the world of being able to exfiltrate those sorts of tokens via cross-site scripting attacks. Again, with cross-site scripting, there's a lot of other things that can happen. So just protecting against that doesn't necessarily protect against everything, but it's still a problem that we're sort of reverting back to by storing these session tokens in local storage as opposed to a cookie where there's other mitigation mechanisms in place. And Ksenia, I hope I'm saying that right, even mentioned yesterday an XSS exfiltration attack against a JOT token. So this is a potentially real problem, and what we've done historically, there's been things to try to prevent against the exfiltration of these tokens, like HTTP only, like secure, but token binding, which I'm going to get into here in a minute, is sort of looking at it from the other side and sort of inoculating the tokens against misuse or reuse once they are stolen. So it doesn't help protect against the actual stealing of it. We have the other things in place for that, but makes them more difficult or even impossible to use if they are stolen. And so that brings me to token binding, which was originally proposed. The work got started in the IETF, the Internet Engineering Task Force, in the token binding working group, and it started about 3 years ago in Dallas. This was a picture I took in Dallas there in the main photo. Up in the right is a little bit more what it really looks like, kicking off a working group meeting, which is a bunch of nerds in a room. Not dissimilar to this, although this room's actually a little bit nicer, and you all, of course, aren't nerds. But what token binding does is it enables a long-lived binding of cookies or other security tokens, OAuth tokens and so forth, to a public-private key pair generated on the client. Talk a little bit more about how that actually works. So because engineers like to break things up and layer them, the core base token binding functionality is broken up into 3 specifications. These are all in draft right now, but they're very, very near the final stages of becoming RFCs. The first one is a TLS extension for negotiating the use of token binding. The next one is the actual, they call it the token binding protocol, but it really is the definition of what these token binding messages look like. So there's a message format that's defined how they work. And then there's an application of this stuff to HTTP, which is really to HTTPS because all the underlying layers are TLS. Talk a little bit about how that works. So in TLS, this is TLS 1.2. I know 1.3 is coming out, but looking at 1.2 here, there is the client hello and the server hello. And this is how the handshake begins. The client sends a client hello, the server responds with a server hello, and a lot of parameterization negotiation that goes along in that. But in addition to, or within each of those messages, there's an extension mechanism where you can include extensions in the hello, and the server can respond with the same extension or variation on the extension, basically acknowledging that and agreeing together that they'll support whatever that extension is in the course of this connection. And token binding TLS negotiation takes advantage of this. And it looks like this. So when the client sends its client hello, along with whatever other extensions it's including, and its cipher suites and so forth, it includes the token binding extension, which happens to be the number 24. And within that extension, it also includes a version, as well as what's called a key parameters list, which is a very confusing name, but what's they called it. And the key parameters basically is a set of, it defines a key type and a signing algorithm that'll be used later. And so it gives some algorithm agility and negotiation ability here. And there's 3 defined right now. One is 2 are RSA algorithms with a key size of 2048, and one's the old PKCS 1.5 signature, the other is PSS. And there's also an elliptic curve on the NIST P256 curve. And those are the 3 that are defined. So the client sends the algorithms that it supports in the extension. The server sees those, checks a few other things, including that extended master secret has been negotiated, and there's a secure renegotiation extension. If those things aren't available, it can't successfully negotiate token binding. If they are, it responds, and it supports token binding. It responds with the server hello, whatever other extensions it has, and a token binding extension message. In this case, it also indicates the version. There's some version negotiation stuff there that will probably not be used in ossify over time, but that's life. And it returns also the key parameters list, but in the response, the list is restricted to only a single value. And this is effectively the server saying, okay, this is of the signature types and keys that you said you could support, this is the one that I want you to use. So in this particular example, it's saying, great, let's do this, and let's use elliptic curve P256. Assuming that piece of negotiation was successful, all subsequent HTTPS requests over that TLS connection send a header, this sec-token-binding header, with an encoded token binding message on every single HTTP request over that connection where token binding was negotiated. And that is an encoded token binding message. And within it, it's base64 URL encoded. Once decoded, it's a binary message that has 1 or more token bindings. Typically just 1, but there can be more. We'll talk about the reasons for that a bit later. In each of those token bindings, there's a type indicator, which is just a single byte that says whether it's the provided or referred. That's some jargon and nomenclature that says whether basically it's the key I use directly with the entity that I'm talking to, that's provided, or if it's the key that I use with another server that's there to facilitate cross-domain use cases, which we'll talk about more later, but typically it's just the provided. There's a token binding ID, which is another weird name, but basically this is the public key and the type put together, and really is just the public key of the key pair that the client generated. So it's the full public key available encoded. And then there's a signature over the type, the key type, and a few other things, and most importantly, over the EKM, which is the TLS exported key material, which is basically a unique cryptographically secure identifier that's contextualized for a specific use from the TLS connection. And then there's some room for extensions. But basically, what this does by signing over that EKM is it proves that the client possesses the private key, and it does so with respect to this specific TLS connection. So the same token binding message wouldn't be valid over another TLS connection and couldn't be recreated by another entity without the private key over that connection. So it binds it to the specific TLS connection and associates it with that key. And one important thing here is that these keys are long-lived and span TLS connections. So even though this might happen and then the connection is torn down, or you close your laptop and go from work to home and restart the session, you'll get a different token binding message because the signature is over a different EKM. But the actual key that you're proving possession of is longer term. So you can bind things to that key and they live a long time. And so the security mechanisms of it are also long term. Probably the most straightforward application of token binding would be to bind a cookie to that token binding key. And this is done by having the server, when it issues the cookie, associate a token binding ID with that cookie, and then check it on subsequent use. Basically just saying, this cookie, usually a session cookie, is only valid when presented by a client that can also prove possession of this particular public key. And then, yes, sir?
What would this do beyond just signing the cookie? The proper question? Or?
Yeah, that's a fair question. So sessions typically are maintained with a cookie, and there's sort of two main ways to do it. One would be to sign content and the information, the server issues it. The other would be to save it server side and associate it. This is different in that either one of those will work here, but it's not the server signing it, it's the server associating that session with a key that the client proves possession of, so that if this cookie is somehow stolen and somebody else tries to use it, they also have to prove possession of the private key of the original client, which is much, much more difficult to do. It's much harder to steal a private key for whatever reason than it would be to steal a cookie.
Can I have a quick follow-up?
Sure.
Will this provide replay attack prevention where a digital signature will not? If I steal a cookie, I can still replay it, right? So will this give me replay attack protection as well?
In the sense that it'll prevent being played by any other party without the key, yes. So the same client can replay the cookie because it's proving possession of the associated key. But if the cookie is ever stolen, it can't be replayed because it's bound to this key pair that only the client knows.
One question about the key. Are you talking about client-side TLS key, or is it something different when you say key?
It's a new concept. I'm sorry, I forgot everyone can hear. He was asking, am I talking about the client-side TLS key or is it a different key? And it is in fact a different key, but it's client-side. So it's not a client certificate like you'd see in sort of traditional mutual TLS, but it is a key that's controlled by the client. It's a bare key. There's no certificate around it. It's just a bare key that the client generates on demand or has previously, but basically it's not distributed or anything. The client creates it as needed and then just proves possession of it over at the HTTP layer relative to the TLS connection on every request. So it's not an authentication mechanism, but it's sort of a trust on first use kind of thing where the client, when it starts communicating, says, hey, here's a key that I control the private portion of and I can prove that I have over time, so that the server can take things and bind it to that particular key such that those things can't be used by someone that doesn't possess the private key associated with it.
The most common message of persistence is a cookie, or how are you going to preserve it on the client?
I'm sorry, can you repeat?
What is a persistence method? Because you're saying it's like long-lived.
Oh, okay, yeah. Oh, the question was, what is the persistence method on the client? And that is an implementation detail of the client. But what we're seeing in the early browser implementations is they basically treat them the same way that they do with cookies. So they don't actually even, they don't even surface it to the user, but if you were to clear your cookies through whatever mechanism it would be, you would also clear the associated token binding keys. And we'll get to it a little bit later, but these keys are also more or less domain bound. So if you, or domain scoped. So if you clear cookies for a specific site, only those associated token binding keys would be cleared from your client as well. And that's the browser use case. So one thing that I think is interesting and promising about this augments existing authentication and session management mechanisms. Unlike client certificates, where basically you get a proof of possession mechanism, a strong PKI-based, public-private key-based authentication, that also comes with identity and trust issues and a bunch of other baggage that makes it hard to deploy. What this does is they're just bare keys, it's negotiated, and the client starts doing it, and it can all happen transparently to the users and begin to add security on top of existing mechanisms. So you can keep your username login, username password login, and begin to augment it with stronger session mechanisms. Start token binding your cookies when available, but only opportunistically. It doesn't have to all be rolled out at once because of the negotiation and the way that there's no sort of, it doesn't have to be a big bang deployment. It can be sort of a slow, phased deployment where those participants that support it can take advantage of it, and those that don't can continue to use the existing model today, which I think will help with adoption over time. So another picture, just being gratuitous. This was another IETF meeting in Chicago, but I thought this tweet was kind of funny that someone said, I don't even know who this was, that they said there's always a new layering violation to implement here at IETF. Which I don't know if they were talking about token binding or not, but they very well could have been, because token binding is a horrible violation of layering. And I say that sort of tongue-in-cheek. I know that, but I also think that oftentimes security problems arise at the boundary between layers. And so while this is a violation, that very violation is what makes it so useful. It binds things together across those layers so that the tricky little space between those layers can't be used to carry out attacks. It also makes it hard to implement, which I think will be a potential blocker for some of this over time in deployment, because you have to be able to work at and get access to different parts of the layering. So it's sort of a double-edged sword. I think it is sort of ugly in its solution space. It does provide value, but that ugliness also makes it a little bit more difficult to implement. So I don't know if you all are thinking this, but a lot of times, at least early on when I would begin to talk about this technology to people and sort of try to evangelize it, people would sort of freak out about the privacy implications. And so I do want to say that this is not some big super cookie or some new Big Brother tracking mechanism. And that's because the keys are scoped. So the client generates a unique new key or reuses one for it, but they scope them to the effective top-level domain +1. I'm glad that concept was already introduced earlier today. So for example, example.com, www.example.com, and etc.example.com, from the browser's perspective, would all use the same client-side generated token binding key. But a different key would be used for example.org, and also another different one would be used for example.co.uk. So it basically has the same scoping and privacy implications as cookies themselves. It's not, which arguably have their problems, but this has the same problem, and it's not making anything worse in terms of privacy and tracking, but it is allowing for improved security around the use of cookies and particularly session cookies. So one of the things that my company does a lot of is cross-domain single sign-on via SAML or OpenID Connect, maybe WS Federation. And so the people working on token binding were aware of these scenarios and built in support or some support for cross-domain single sign-on. And there's an HTTP response header that will tell the browser that it should reveal the token binding ID, that's effectively, again, the public key, used between itself and the relying party, the site that we're trying to go to sign into, in addition to the one that is being used between itself and the identity provider. So that's basically saying when you start at the relying party, you realize you need, building slides sometimes get me. And there's also needs to be generic token binding implementations are suggested that they have some ability to send this referred binding based on other signals or perhaps something in the API. The idea is basically that sometimes when you contact a site, you need to prove possession of this key that you're normally using with that site. But there are other times where that particular site might be an identity provider or an OAuth authorization server that's going to be issuing tokens that you will use somewhere else. And this this header and referred token binding basically allows you to send 2 token binding IDs in that initial request and allows that server to bind to the other key so that when you use whatever that token is at the other party, it'll also be bound. And that works like this, basically. When you start at the relying party and it needs to send you over to an identity provider to authenticate you, you include this, include referred token binding ID header, set it to true, and that signals to the browser that when it makes this request to the identity provider to include the token binding header in there, but this time it has two bindings, both the provided and the referred, and this allows the identity provider to do its own binding of its own session cookies or whatever to the provided ID, but also use the referred ID to bind something in that token that'll be consumable by the relying party. It's the key that'll be used when you come back over to the relying party, and it can be, and so it allows the, sorry, I'm talking all over myself. It allows the identity provider to bind to the key that'll be used over here, which gives you the same kind of protection mechanisms, but across domains. Yes, Jim?
And this assumes that the identity provider and relying party already have some kind of cryptographic agreement or relationship.
Absolutely, yeah. We'll look a little bit at actually the details of this. This is just showing the mechanism for sharing the token binding key. It doesn't replace any of the existing sort of single sign-on mechanisms, it augments it. So there still has to be a relationship. The token that's actually sent back from the IDP to the relying party needs to be signed or otherwise protected or whatever. This is just an additional mechanism that binds, that allows the identity provider to bind that token to a key held by the browser, which is on top of the normal functionality where the identity provider signs the token and the relying party verifies that it came from the identity provider. This binds it also to the browser, so if somehow during the course of transit or whatever it's stolen, it can't be played by another browser. I want to do a quick interlude on JOT, JWT, or JOT. You're supposed to pronounce it JOT. A lot of people say JWT. It's confusing as hell, really, but it lets a joke like JOT or not be thrown in there. Talk about it real quick. This is a JOT. It's a 3-part base64 URL encoded bit of JSON and binary. And basically, this is JWS. So this is only a signed token. There are also encrypted tokens, but I'm going to just talk about signed for simplicity here. This has a header, which has a few things. It basically says the algorithm that was used to sign this and a little hint about what key was used to do it. There's the actual signature, which is just the application of that algorithm over the whole rest of it. And then inside of that, the actual signed protected material is a bunch of claims, which is really just JSON name-value pairs, sometimes more structured than that, but typically just names and values that say things like who issued it, who's it intended for, when it expires, and who the subject of the token is. Who is this about? So in the single sign-on scenario before, this would be issued by the identity provider. It'd be audience to go to the relying party, and would it be about me, the subject of the transaction? I don't know what people have read or know. I know there's been some hot takes on JWT and the underlying JWS specifications and so forth. Some of them are legit. I think a lot of them are overblown. I think when used properly, this technology is really valuable and it can be used securely and provide a lot of value. So it's my little take. Although it does get misused like many other technologies, I don't think it's inherently flawed to the extent that some have said. But anyway, I'm going to use JOTs in some of the subsequent demos that are things that I'm going to show. So I wanted to just kind of lay that out there, kind of the basics of how they work in case some people weren't familiar with it. So then there's, we talked about binding to cookies. There's also a formal specification that talks about how to do cross-domain single sign-on for OpenID Connect with token binding. So this is a sort of an extension specification to OpenID Connect, and it describes basically how to use the referred token binding and the signaling header to do exactly that. It utilizes the include referred token binding ID header and the referred token binding. So basically the relying party or the client in Connect parlance sends that header to the browser so that the browser will send the referred token binding to the IDP or the, what do they call it in Connect, the provider, the OpenID provider. That provider takes that referred binding and binds the ID token, that's the JOT that is used and sent back for single sign-on, binds it to the referred token binding ID, and then so that binds it again to the browser that holds the key. And what it does is it uses a new claim, another little bit of JSON that is basically the CNF claim that means confirmation, and another cute short name of TBH to say this is the hash of the token binding ID key that I need the client when presenting this JOT to prove possession of that associated key. And so I'm going to show a demo here. It's in quotes because I'm not either brave or stupid enough to actually do a live demo, so I do a lot of screenshots here. And it's going to show basically two things. It's going to show a bound ID token SSO doing the OpenID Connect flow I showed before, and then the relying party is going to establish its own session based on that SSO and in turn bind that cookie. And sort of the pieces here are we have an identity provider that's at idp.example.com and a relying party at rp.example.io. And this relying party is actually just like it's a reverse proxy that's doing access control. And just for the sake of like showing what it's doing, it's proxying to this http.ben.org. So it just basically takes whatever request comes in and echoes it back out as JSON so you can see what's going on. So we get started. The first thing that happens is there's an unauthenticated access request to the RP that comes in. It's a get to rpexample.io headers. And you can see that we didn't see the TLS negotiation, but the sec token binding, I apologize, this is small. The token binding header is here. So we've negotiated token binding with this relying party, and the browser client is then sending the token binding header here. But that's not authentication itself. It's just proving possession of that key. So this is unauthenticated. There's no session cookie or anything like that. So the relying party is going to redirect off to the IDP for authentication. So we get a 302 authenticating and sends it off to redirects to the IDP right there. And then maybe most importantly here, right above that, it includes that include referred token binding ID header, which again will signal to the browser client to send both token binding IDs to the IDP. And we say that here, here's the request, the GET request to the IDP, and it sends the sec token binding header here, and you can see just by, it's a bunch of base64 encoded garbage basically at this point, but it's significantly larger than the last one we saw, and that's because it contains two keys in it, and proof of two of those keys. One is the key that's used here with the IDP, and one is the key that's going to be used with the relying party, and by providing that one, it allows that IDP to bind it to that key when it issues the token. So once we authenticate, we redirect back over to the relying party. In this case, it's through a form auto post, but there's a lot of different ways to do that in Connect. So we get a post to the callback URL or the redirect URI of that particular client. And again, we see the token binding header here. This time it's only the single binding that's used between the client and this relying party. And then we get the post data contains an ID token, which in turn is just a JOT. And I'll show the decoded JOT content here. You got the header, you got all your claims information, and perhaps most importantly for this example, we have the confirmation claim and the token binding hash confirmation in there, which is a hash just of the key within that message. So in delivering this token, the client has shown up, proved possession of the associated key by sending the header, and then delivered this token that's meant to represent the authentication of the user that is in turn bound to that key. So we have really, really high confidence that the presenter of this token is the one that is allowed to do it, that's expected to do it. So proof of possession of associated key in order to do the sign-on. And then as a result, we successfully validate that, and the relying party then sets its own session cookie, which you can see here in a set cookie, and redirects back to the originally requested resource, which is to see this headers page. And another request comes in. It is a get to that particular resource, again, sending the token binding ID. In this case, we're the browser is playing the cookie as a session mechanism, and this too is being represented as a JOT. In this case, it's a signed JOT because it's a little bit easier to see. A symmetrically encrypted JOT is probably a better token to use for this case, but I did this just for example. And that particular cookie then is bound to the same key. So we have a token-bound session here that couldn't be used by any other browser, even if the session cookie is stolen. And then just showing a little bit of what the reverse proxy that's doing access control is doing here. Not only does it check the token binding key, it pulls some user information out of the JOT and injects it into headers and sends it to the back end, which in this case is just echoing it back to us as JSON. Yes?
Yeah. There's one, I know you're focusing on the protocol here and how things get from one side to the other.
Yeah.
But I guess in the back of my mind, I've got how are thousands of key materials going to be distributed amongst all the different web browsers? And I'm assuming they're going to have to do some sort of CSR and generate a request to get some sort of certificate that change back on different partners.
Yeah, so that's a really good question, and let me try to repeat it. One is basically, he said, you're doing a lot of protocol details here, and that's great, but that's sort of stupid because the real problem is going to be key distribution. How do the clients get all these keys? Is that a fair?
I didn't use the word stupid.
I interpreted it though. I was trying to make it funny. You called me stupid. No, no, it's a really good question because one of the difficulties, and you could argue we already have technology very, very similar to this, and that's client-side TLS. And browsers can do that today, but the user experience is horrible, and the operational experience is maybe even worse in terms of distributing and managing and renewing those certificates. Not the key. One of the main key differences about token binding as opposed to that is these are not certificates, they're raw keys, and they're not distributed. They're generated on demand by the client. So there's no need for distribution. It's basically the client creates a key when it needs it and starts using it. And the server doesn't authenticate against that key. It just uses the fact that the client proves possession of that key so it can bind tokens to that specific client so they can't be used from anywhere else. In a way, you can think of it as like, maybe really cryptographically strong and less error-prone method of browser fingerprinting. So a lot of times a session cookie will try to be browser fingerprinted a little bit or associated with an IP address. So if it gets used from somewhere else, they can reject it or do something. But those techniques are terribly hard to do and error-prone in both directions. This is doing the same kind of thing, allowing you to associate a session cookie with a specific browser, but doing it using public-private key cryptography so that it's very strong and it's not prone to either false negatives or false positives. But that's a long way around saying there's no key distribution problem because it's client-side generated keys. Whoa, lots of hands. Ksenia. Wherever the client wants to store it. It's a good question. So as far as I know, there's some early implementations of this in browsers, and they're software-based keys. And they're protected as well as other assets on the machine and software. There are also, I think, plans, or at least the idea that these keys could be stored, in a TPM type device, whatever the trusted computing module or I don't know all the right terminology, but like the local hardware security module on a phone or something like that. And that's actually one of the reasons why PKCS 1.5 RSA signatures are supported is the expectation that some of those hardware key modules need that in order to be able to function. They can't do PSS or elliptic curves. So the specification doesn't demand one or the other. There's certainly the potential for higher value systems to store those keys in hardware such that they can't be protected. And my feeling though too is that even if they're in software, they're going to be significantly better protected than the tokens that they're meant to protect. So a lot of the things that we're seeing now is bearer tokens being stolen because they're easily exfiltrated because they're supposed to be sent other places, so they're not tightly protected. And so it's not perfect, but protecting the keys in software, I think, is still a significantly better step. Yes, sir.
I've seen where session cookies are associated with the TLS session ID, and they're only valid for that SSL or the TLS
Yeah.
connection. Can you enumerate some of the advantages of this over doing something like that?
Yeah, the biggest one is the longevity of it. So that lasts as long as the TLS session, which many times are very short. Like in the course of browsing or messing around, like if you take a break, it depends on the timeouts and things, but the TLS session's often torn down in a matter of minutes and reestablished. Whereas these, because the EKM can be thought of sort of like a unique identifier for the session, but it's being used as sort of a transitory bit of proof relative to that connection of possession of this public-private key pair. So if you bind, sorry, I'm having trouble explaining it. Binding to the session is relatively short-lived. Token binding binds to a key on the client, which can be very long-lived. So you can issue a cookie a session that's longer-lived and continue to use the same keys so that if you establish a new TLS connection, you'll get the same binding, the same benefits. You won't have to log in again. If you log in and, at work, do some of your work, close down your laptop, go home, and then try to pick up the work there again. If you were binding to this TLS connection itself, you'd have a new one, you'd have to log in again. If you're using token binding, it's bound to the other, actually to the key, so you can get the same protections, but resume your work and not have to log in again at that point.
Fundamental question. We used to have OAuth 1.0, and we didn't have this problem with bearer token because you could not use token without signature, right? And then suddenly everyone had decided that it's bad, it's like a lot of maintenance, we don't want to use it, and OAuth 2.0 wasn't better. Now we are saying, let's just go actually the same, but at TLS level, and the question is why this is better? Because nobody is going to write TLS extension in any organization. So why this is better than OAuth 1.0?
So the question was, again, I think there's a "why are you stupid" in there. I'm kidding. was that OAuth 1 had signatures. It had a proof of possession type of mechanism that came with a lot of problems. And they weren't actually in the signatures themselves so much as in the canonicalization and normalization of the request and the URL to be signed. And getting away from that and pushing the security of the TLS layer was a big motivation behind what was done in OAuth 2. As well as the ability to support different types of clients. Another thing that happened in OAuth 1 is that signature was not just part of the token, but it sort of combined the token and the client identifier into the key material that signed it. And it had a ton of operational and deployment problems that people had. I will talk about this a little bit more later. It's sort of, I guess it's sort of philosophical that if and when the underlying infrastructure and APIs are available to do token binding, getting the proof and possession mechanism then into the tokens and dealing with it at that layer once the underlying APIs and TLS stuff is in place makes it super, super simple to do. And that's kind of consistent with the philosophy of OAuth in the first place, OAuth 2 in the first place, which was to defer as much as possible of the security onto the TLS layer because there exist a lot of robust libraries and functionality for that rather than trying to build it into the application layer. And that, I think, will continue to be true here to the extent that TLS stacks and APIs allow for this kind of functionality to exist. And that, quite frankly, is a question whether that will happen and on what time frame.
But does TLS community support you to build this extension to their protocol and do like a major implementers like OpenSSL? Will they support it?
I hope so.
Because if they don't, it's like
It's a fair question. I'll talk a little bit about the landscape of support a little bit later. But there are some pretty significant players involved, Google being one of them, and Microsoft. It's not in OpenSSL yet, but there's some extensions to OpenSSL that make this possible that are currently available. The specification itself is going to register this extension with the IETF TLS extension registry. There are people working on TLS that are also working on this. So it's not a sure thing by any means, but the right kind of people are involved and the right kind of organizations are involved that give me some hope that it will be adopted. All right. Oh, I thought this was funny. When echoing back a bunch of base-64 URL encoded information, Chrome would occasionally ask me if I wanted to translate the page from Polish. I don't really know what that means, but there's a lot of talk about AI and how powerful it is. But as long as these things are happening, I don't think the bots are taking over the world just yet. So that's the end of my demo. I didn't have my own photograph of a dog and a pony, but I thought a unicorn playing a guitar would kind of sub in for that. So that was OpenID Connect, cookies being bound. There's also token binding for OAuth 2. And that's itself its own specification being developed in the IETF inside of the inside of the OAuth working group. Real quickly go over how this works. Basically, it binds access tokens with that referred token binding ID, as maybe you could guess. It's binding to something that some other site will be using, or the connection between the client and that other site. It talks about how to bind refresh tokens with the provided ID, which is actually really similar to the cookie binding case. The refresh token only ever goes between the client and the authorization server that issued it. So binding to the key that's used on the connection between those two entities makes sense. There's some stuff to bind authorization codes using extensions of Pixie, which is it's interesting. I can say that because I wrote some of it. We'll see. And then there's also token binding for JOT-based authorization grants and client authentication. I just want to talk a little bit about token binding for access tokens. This is arguably one of the most useful applications, and it prevents the use of lost or stolen access tokens. Again, it inoculates these tokens from being used by a party that doesn't possess the associated private key. Access tokens are a lot like cookies, except for all the ways that they aren't. In the early days of OAuth, there were a lot of comparisons drawn between cookies and access tokens, and as a result, sort of justifying the fact that they were bearer tokens, that was okay, because cookies are bearer tokens, and that's been mostly okay, and these are access tokens, they're bearer tokens, they're a lot like cookies, so that's probably gonna be okay as well. More and more, though, we're seeing that access tokens aren't exactly like cookies. They don't have the same single origin protections. And depending on the use case and the client involved, the client might be sending them to different places. If the client's dynamically discovering those resources, there's various attacks that can be levied against it. So there's I think, growing need for stronger protections on access tokens. Another thing it prevents, which I think is pretty interesting, is it's a protected resource, the API or whatever that's actually accepting the access tokens from using the token at another protected resource, because it's bound to that client. You can't suddenly have a malicious API or protected resource that starts reusing tokens against another protected resource. This is a little bit to your point, is this isn't the first time we've tried to do proof of possession for access tokens. We had it in OAuth 1, sort of. I mean, we did, it was different, but it was there. There was a big kerfuffle right before the publishing of OAuth 2 itself, where the editor wrote a really passionate blog post and quit. I can see both sides of that, but it was because, basically, largely because there wasn't native support for some kind of proof of possession mechanism in the core specification itself. A while ago, there was an attempt to redefine sort of the OAuth 1 style model a little bit by doing HTTP request level signing in OAuth, which it's still out there, but it's sort of petered out. There's another standard that uses client-side TLS to do much of the same kind of binding here, which is, it's interesting. It's actually something I'm working on. It's out there largely to support new open banking API initiatives, largely in Europe, that need some kind of proof of possession mechanism like now. And while I think token binding is really promising, it's not ready for prime time. It's not ready to be deployed where mutual TLS is. So it's not a new thing, but this maybe offers, this is what I said before, token binding of access tokens is really easy except for all the hard parts. Yeah, what the fuck was the question I'm supposed to repeat. And that is to say that once the APIs are in place at the underlying layer, once your TLS stack and maybe your HTTP stack support this stuff, doing this from the client side or even the server side is like, it's crazy easy. It's like a super simple way to do bound tokens. But until that stuff is in place, it's really hard or almost impossible. It's not something that the average developer can just go start building themselves, because you need access to all these different layers, and oftentimes layers that either aren't accessible or not easily accessible for your average developer, or most developers. Just a quick look at what that would look like, because I like writing that's too hard to read and pictures. Token-bound access token, there's not much to it when you look at it. In this case, the OAuth client makes a request for a new access token to the authorization server. In this case, it's presenting its refresh token, and it sends the sec token binding ID, or sec token binding header here that has 2 token binding IDs. The authorization server takes the referred token binding from that, binds the access to it using this. If it's a JOT, it would look like this. The CNF claim carrying the token binding ID hash. And then the OAuth client turns around and uses that, and all it needs to do is send that token as it normally would, as an authorization header, and then that token is in turn bound to its token binding key, which is proved possession over over the TLS connection by sending this header. And so the authorization server binds the access token to the referred token binding, and then the protected resource of the API validates that access token as it normally would, but then adds the additional check of comparing the hash of the token binding ID to the one that was proven possession of over that the special sec token binding header. I just sort of thought this picture was funny. The threat landscape here is vast and complex, and token binding, I think, has the potential to solve a lot of problems. But I think, sort of carrying back to your question about where the key is stored, it can't solve everything. You know, if a client is malware infected, depending on how the keys are stored, maybe those keys could be exfiltrated. Maybe even if they can't be exfiltrated, potentially there's access to use those keys to sign in while the thing's on there. So a lot of the protections come down to how well the keys are protected, which is a whole other realm and problem space of its own. But in terms of just the HTTP level interactions, this offers a huge potential to upgrade security for the use of tokens. A question I started getting a lot is, that's great, this happens between the client and whatever terminates TLS, but applications never or rarely are the ones that actually terminate TLS themselves. So I'm working on and pushing for a specification that will describe how token binding can be deployed in reverse proxy type deployments or load balancer type deployments that are doing application layer load balancing, such that whatever that front-end component that's terminating TLS can share information with the back-end application about the token binding that was done that allows that application itself to bind the tokens. So this looks like the client doing normal token binding between itself and what it perceives as the host. It has no idea what the deployment architecture is. It just sees the host there, it negotiates token binding and sends the header. The reverse proxy or TLS terminator, whatever's doing that, validates the token binding message itself, sanitizes headers as need be because it's a reverse proxy, and then passes the actual, just the encoded token binding ID. It takes the signature and all the superfluous stuff now that the validation's been done, and just takes the ID and passes it in a new header back to the origin server, the application server, and that backend server then can validate or issue cookies or tokens based on that ID as needed. And the hope here is that unlike client-side, client TLS, mutual TLS, where there's no standardized defined way to do this, and all the app server or all the application servers like Apache and Nginx do it a little bit differently to share the client certificate with the backend. The goal here is to standardize a way of doing it so that everybody does it the same and hopefully supports it as well. Yeah. The question was, do any off-the-shelf reverse proxies support this yet? And let me start by saying it's still really early. The standards aren't even ratified RFCs yet. There are, I know there's a module for Apache that does this, and some extensions of Apache that does it. There's some work in Nginx that does something like this. I don't think it conforms to the standard yet. So there's a little bit there. Somebody, when I presented this work at the most recent IETF meeting, somebody said that Facebook was doing some of this internally, although that's not really help for interoperability, but not out of the box. There's some extensions. It's looking promising, but it's still early. 5 minutes, that's good because I'm almost done. I just want to talk a little bit about sort of the landscape of the whole technology. Those three sort of core IETF token binding specs are soon to be RFCs. I will say that IETF time is not dissimilar to island time in that it's a little slow, but they're getting there and they should be published RFCs soon. And hopefully this will be sort of the impetus to help adoption and support in APIs, because I know a lot of products and APIs and stacks or whatever are hesitant to support things before they're fully standard. But there is support for some drafts. Google Chrome and Microsoft Edge and IE support various draft versions of this. I haven't played with Edge, but Chrome has it behind a feature flag. You can turn it on and see it working now. Google itself turned it up on their servers in January, actually, and this is an old site, it was January of last year, and they have it live on all their server infrastructure. The .NET framework introduced some support for on the server side in 4.6, and there's some open source stuff available already. One is I'm not even sure what it is with OpenSSL. I guess it's an extension to OpenSSL that allows you to do this. There's an Apache module, there's an Nginx module, and just recently I've published, because I work in Java, for better or worse, some Java extensions that allow the negotiation piece to happen. Yeah?
You said global Google service. Does that mean that all Google cookies last time we have been token bound?
I'm sorry, say again?
Global and Google service, does that mean Google has actually been binding the cookies, or it's just that it supports it, but not necessarily using it?
I don't actually know. I think they bind some of the cookies if they can. I'm presuming they do it opportunistically. So if the client negotiates, they will bind it. And I know they had some interoperability problems with Microsoft as various versions rolled out, which makes me think they're doing more than just checking it, that there's some live functionality here. But I don't know the specific details of it. So like I said, there's some newish Java support there, which has been interesting. I've worked a lot on that, but making it available for the community, hopefully, and also because it's required by their license. The OpenID Connect token binding authentication spec is coming along. I think it's dependent on some of the underlying ones, but is looking good once those things sort of fall out. The OAuth stuff is also coming along, although it's a little bit more problematic in terms of I think it needs the implementation experience and feedback that is going to be hard to get, a bit of a chicken and egg until some of the APIs are available. And the reverse proxy spec that I'm working on was recently adopted by the working group, which doesn't guarantee anything, but it is an important step in the process of becoming an official standard. Yes, sir.
With the advent of like TLS 1.3 and features like long-lived sessions, how do you anticipate like some of that might impact this architecture?
Hopefully not very much at all. So I don't know a whole lot about the long-lived session and session resumption mechanism, but it's really decoupled from that. There's a different name for the exported key material stuff, but it's the same functionality and the same exact. It's a different name, same stuff under the different name. So you still get that key material from the underlying connection and sign it. And so it's really the same model. The negotiation happens a little bit differently in that the client hello is still in the clear, but there's an encrypted server hello extension, so it'll be in there. There's actually another spec coming along behind all this that defines how to do negotiation in TLS 1.3. It's practically the same thing. It's just sort of mapping it to the new places in the protocol. But in terms of sort of the overall flow and functionality, it should be exactly the same, or close enough to exactly the same. The main exception to that is how and if it will work in conjunction with the zero round trip stuff of negotiating a new session. And that, frankly, it's beyond me what the right answer is there and where things will end up. There's people that say it shouldn't be supported at all. There's people that say we need to allow for it. And it's sort of an open area there. But as long as you're doing at least a back and forth handshake, it's basically the same with 1.3.